Okay, okay.
Okay, so for the second talk, we have Karan who will tell us about soft factorization and ADS spacetime.
Okay, yeah, so I'd like to thank the organizers for this opportunity and for this amazing conference, actually. So this is work that I've done with, in collaboration with Nabamita Banerjee and Urpita Mitro, who's a postdoc in South Korea, and it's based on these two papers. So I'll first give the overview on motivation quite briefly, and then I'll talk about two independent derivations of this soft factorization in ADS before concluding with an overview with respect to like other results which are known in the literature and future directions. So really rapid summary of something that's been discussed here and in an extremely simplified setting is this. You can talk about single soft theorems on flat spacetime. Okay, so these describe the factorization of scattering amplitudes of higher point amplitudes to lower points. So if you have one soft particle, then in the soft limit you have a soft particle times the hard amplitude. Now the soft factor, as we've seen also in this conference, is it has a frequency expansion, which is quite interesting. And for this talk, I'm just going to talk about the leading factor. I'll stick to the soft photon case, even though there are results for the graviton in our paper. And of course, there's renewed interest in soft theorems, in large part due to its relation with asymptotic symmetries and holography on asymptotically flat spacetimes. And we've had the review talk by Laura on this. Okay, so I'll just talk about one aspect of soft theorems which will tie to what we're going to be talking about. Of course, there's many more, but so we have the soft factor, and in the case of the leading soft factor, for which I've put this this 0 over there. So the leading soft factor can be rewritten as a large gauge Ward identity, and this is parameterized in the case of massless scattering. So it's all massless particles, but like one of them is taken soft. And in that case, this epsilon is given by like 1 over z minus z. Okay. And at this point, we of course have many results known to subleading orders. There have been many talks in this conference, in particular by Sylvia, Sangmin, and Shreyans. Okay, so why are we interested in this? We would like to know what the generalizations of soft factorization are on non-asymptotically flat spacetimes. And one of the simplest extensions we can think about are on those with the cosmological constant. And of course, what makes them particularly tractable is that you can identify flat spacetime limits where you can define scattering amplitudes. A priori, obviously, you don't have them, but in this setting you can, and there have been amazing talks in this conference on this topic. Now, if we can address soft factorization appropriately in ADS, we might get a better handle on flat spacetime holography, which was a motivating force for us at least. And so the story so far, and part of this is what I'll be discussing today, is the following. So Weinberg soft theorems are derivable in the flat limit from CFT Ward identities, for example. So I've written CFT3 here because it's in 4D, but this is work by Hijano and Neuenfeld. We can then, so what we were able to show is that there are these inverse ADS radius corrections to the flat soft factors that you normally have, which are definable. So you go to the flat limit, you have your S matrix over there. You would have like these corrections to the conventional flat spacetime soft factors. And we derive these in two different distinct approaches. One is through these classical soft theorems, which were formulated by Sen, Sahu, and many people in this audience right now. And we also have the derivation using the CFT3 Ward identity as done by Hijano. So I'll really quickly go through the classical soft theorem derivation, and I'll just stick to the steps and the results. If you guys need any further details, you can meet me afterwards. So classical soft theorems essentially give you universal contributions to soft photon and graviton factors from soft limits of classical radiative solutions. That's the selling point. And they're applicable in a few settings, but the setting we'll talk about are in these probe scattering settings where we have the change in the scatterer is very small before and after the scattering, while the wavelengths are much larger than the impact parameters. Oh, that's so it's this is just the change. So yeah, there isn't like this is not like some ultra relativistic scattering or trans-Planckian thing or.
So my question, delta E has units of energy.
The rest mass that you would have in your problem. So okay. So okay, that's what you're asking. So so what you do is you derive this from the energy flux. You will calculate. You have your classical scattering solutions. You'll have your energy flux, and if you take the omega going to zero limit, you can derive these two relations. So you'll have A and E, which are your electromagnetic and gravitational solutions, and these will essentially give you these soft factors. So in our approach, we've also done a probe scattering process, but there's basically three main changes essentially that show up. The first is there's a hierarchy of length scales. So we have an ADS radius, so that now is here. So R is bounded by L above. So this introduces the corrections that we just spoke of. The second is that you have to take a double scaling limit. So one of these will be manifest in the ADS case. We will see that you need to always take omega vanishing as L goes to infinity in order for consistent definitions there. So this gives you this gamma to the 2n corrections, okay, minus 2n rather I should say. So it's a combination of omega and L, and these will correct your flat spacetime soft factors. So there is no like novel scale which is showing up. It's like some perturbative, some small perturbative correction to flat. And lastly, you may wonder obviously that you may have corrections to the trajectory, right? Like you have flat spacetime asymptotics on ADS, that's clearly not the case. But what happens is that these corrections which you'll have, L square, 1 over L square, 1 over L to the 4, these all correct gamma to the minus 4 onwards. Okay, so that's something to keep in mind if you want to like, that's where the ADS potential becomes relevant. So we haven't talked about that, but that's something to keep in mind if you want to extend this program further. So what we've done is we've derived the leading and sub-leading soft photon factors along with their leading 1 by gamma square corrections. Okay, so not higher than that. And in particular, the gamma square corrected result for the soft photon case is shown, can be also shown to satisfy a large gauge ward identity of its own. So to address that, I'll just summarize what's going on here. So you have like this leading factor, you get something which is the usual flat plus the ADS correction, which has this 1 by gamma squared. And from this, you can infer a single soft theorem. So there's A plus some A tilde, which will go with this SL. All right. So this is something that can be inferred. And then if you parameterize for massless particles as before for this factor, you end up with this prediction. Okay. I think I've missed, there should be an n over here, sorry. There's some up to some overall numerical constant which cannot be determined from classical soft theorems. You get a prediction for this being the ward identity like relation that you have in this case. Okay, so I'll now get to the second derivation that we have, which follows this approach by Hijano and Neumanfeld. So it's an analysis in global ADS, and you can get a flat spacetime limit in the usual way. You scale, you rescale by L, all right, and then you can take the L going to infinity limit and you recover the flat spacetime. This is some patch which is centered around the center of global ADS in these coordinates, and you can study field modes, field solutions within this framework, and you get an identification of flat spacetime regions with ADS spacetime regions. So that's the following. If you study massless particles, you will find that they essentially localize, I mean, in the soft limit, they will localize about this tau is equal to pi by 2 for the future, and tau is equal to minus pi by 2 for past. Massive particles will have these as their asymptotic domains, and it relates this Euclidean cap with I plus and I minus. Okay, whereas space-like particles, their domain is basically in this region over here, between pi by 2 and minus pi by 2. Strictly speaking, I've drawn like some flat Penrose diagram, but it's essentially a point. You're taking this L going to infinity limit, and if you shoot time-like particles, space-like particles, and null rays, you will see where they should map onto. Yeah, so I mean, this is like it's not a fateful geodesic. It's a cartoon, but yes, I mean, within this you would have like flat trajectories, but beyond that there will be the ADS potential to be. It'll have this. Yes.
It doesn't have to be on the cut. Right?
It doesn't have to be on the cut. You cut it. You forcibly truncate it here, and you do an analytic continuation.
This is only if you want to view it as an on-shot process.
Absolutely.
But if you want to compute correlators, you can set it anywhere you want along
yes.
the boundary and
Yes.
produce correlators.
Yes. So, yes, that is not done within this framework. But that's an open issue, and I think that can be addressed better within Witten diagram approaches. So I'll get to that towards the end. Okay, so that summarizes that part. And okay, so now I'm just going to go over like what the assumptions are. You have a bulk gauge field. I think I didn't. Oh, okay, fine. It's mentioned here. Yeah. So you have a bulk gauge field, and x will denote like the bulk coordinates, and we are having magnetic boundary conditions with no Coulombic sources. So this reflects the massless scattering that we just talked about, with only one of them being soft. We can do an HKLL reconstruction in terms of these vector and scalar kernels, okay, and they have different dimensions. We can expand the kernels about L going to infinity, and from that we can get a systematic corrections of flat and L square corrections and so on. And we are just going to be interested in this guy. And lastly, we need to take the flat limit. So there's a discrete sum over energies which can be traded for continuous frequencies if you make it scale like L. And so that's what happens here. Accordingly, we have A flat and A L. These are all about flat space-time. Okay, so you can see that this L inverse has a gamma squared, and there's a common angular momentum contribution, which is this. The spherical harmonic contribution, which is this. All right, and so now those are flat bulk solutions, okay, in terms of boundary currents. So we can put them in the usual flat formula, and we basically find flat spacetime and perturbed flat spacetime modes in terms of the boundary current. That's the point. And what you'll see here is that the flat has the correct 1 by z minus z prime that we noted as the gauge parameter for the usual large gauge word identity, but we see that we have this funny looking integral which almost looks correct, but there's an integral over the classical soft factor that we got previously. Okay, so one thing you can do is like a collinear kind of expansion of this. We take z minus z prime to be a minimal distance and expand accordingly for both z. I mean, we can expand this integrated point about this as a minimal distance. And when you do this, it has good features. It diverges like omega inverse, and it has the collinear divergence property that you expect from the soft photon factor. Accordingly, you get the previous thing as the classical soft theorem gauge parameter plus quote unquote corrections. These corrections, curiously enough, go like derivatives of this collinear soft theorem gauge parameter. So finally, how do you get to the soft theorem? You use the U1 word identity. So when you use the U1 word identity, this and this is a time ordered collection of hard operators. They will go to the S matrix, okay, and alpha gets localized to that Scry region around tau is equal to plus and minus pi by 2. So those you identify with the gauge parameters you may have in your problem. So if you take it to be epsilon, you recover the Weinberg theorem, and if you take it to be this, you recover the corrected soft theorem. But of course, in the case of corrected soft theorems, I should mention that there are these additional corrections that we ignored. So that gets me to the conclusion. We found that there is a consistent way to derive these gamma inverse squared soft factor pieces, but it will be important to do this derivation using Witten diagrams to have a more concrete understanding of how boundary correlators go to a factorized S matrix in the bulk. One of the reasons this is interesting is that recently this picture that I just showed you about flat with these tau pi by 2 and Euclidean caps and all that business, this Lorentzian ADS CFT picture, there's a way to extract a CCFT sector within the CFT at those tau is equal to pi by 2 and minus pi by 2 regions. That's a paper by Leonardo de Goya and Ana Maria Raclariu. So it's interesting to ask what happens if you consider these kinds of soft factor corrections there. Lastly, of course, there's a known slogan within the work of Arthur Lipstein and many others around here that soft and flat limits do not commute if you consider the factorization of boundary correlators, famously. And a curious observation is that the soft followed by flat has these derivatives of the gauge parameter involved in there. I believe, not of the gauge parameters, you guys have the polarization. So it's interesting to ask if the two are somehow related. And so could a resummation of these factors that I just told you about hypothetically relate the two limits? So with that, I'll end, and I thank you for your attention. Yeah, sorry if I sped up in the end.
You didn't seem to be used anywhere the fact that J mu was a CFT current, or did I misunderstood?
No, J mu is a CFT current. But
why did you use it?
Oh, sorry. We used it in this ward identity part. There's your J mu.
Here you're using conservation of the U1, not that this is a U1 current. Why did you use this as a CFT? It looks like it's a bulk computation with no reference to
essentially, CFT. Yes. So that is where we are currently working on this part of the problem to have that done more concretely. So we would like to have a full-fledged extraction from boundary correlation functions of an factorized S matrix. It's more complicated than we assumed, so it's still going on, but that's basically where we're heading with this. This is just HKLL for indeed a boundary J related to some bulk soft mode A.
Yes.
That's
so it was in a sense a bulk computation that sort of extends
the
flat soft theorem, but including the fact that it's an ADS.
That's it. ADS. Yes. So that's a deficiency of HKLL as a whole, but we would like a proper expansion and yeah. I mean, I see. Okay, we have to check this, but basically it would compete when this, these quantities are always small as well, these additional pieces that you get, and gamma squared is small by construction, but this would be as they get closer to the boundary, I presume. Like at that point they should, but as we've discussed, I guess there may be some intermediate scale where that may show up. Yeah. Because even though we do a double scaling limit and we say gamma is equal to large, strictly speaking, it's L going to infinity and omega omega is always less than L. Like it's never going to be like omega L is, it's never exactly hitting the boundary. So, yeah.